Thank you. So thanks. I'd like to thank the organizers for putting together this very interesting workshop. So today I will ask a relatively existential question. So what are we really doing when we do geophysical fluid dynamics? So I will first try to convince you that there is a question, and normally I should, when I ask this kind of question, I should define the terms in the question. What is geophysical fluid motion? What is Newtonian? And then go through and arrive at the answers. But basically, the final result of the talk would be the answer, but also the definition of the terms. But when I say Newtonian, I would just want to specify that I'm not talking about viscosity here, right? I'm just saying Newtonian in the sense of the principle of inertia and Newton's fundamental principle of dynamics and things like this. Okay, so let's try to think about what geophysical motion is. So it takes its roots in classical hydrodynamics. So Newton's fundamental principle of dynamics. We have acceleration equals to sum of forces. So this is the gravity, right? V is the Newtonian gravitational potential, and this is the pressure gradient. And we have some transport up there, down there. If we want to do geophysical fluid dynamics, we'll probably prefer to an inertial frame, we'll prefer a rotating frame, right? So we'll place ourselves in a frame that's moving with the planet. And it's well known that when you do that, you have apparent forces arising. So we have the solid body rotation of the planet will give rise to the Coriolis force on one hand. So this is 2 omega, the curl of this solid body rotation. And it will also give rise to the centrifugal force, which derives from a potential and can be lumped together with the gravitational potential to form the geopotential. So this is all well known. So I would say that at this point we are still not doing geophysical fluid dynamics because we also need to accept the fact that the atmosphere and ocean are thin layers over more or less spherical body. So people for a while have used coordinates that fit this body, and so typically the third spatial coordinate will be vertical, defined as along the gradient of geopotential. And the first 2 coordinates will be horizontal, which means tangential to these surfaces of constant geopotential. But at this point, we have still just rewritten the same equations again and again, just changing variables, changing frame, and nothing new has happened. So I would argue that you really start doing geophysical fluid dynamics when, on top of that, you introduce certain approximations. Some of them are in geometric in nature. I will talk about that immediately again. Some of them are more dynamical in nature, like incompressibility or hydrostatic approximation. And while up to this point we could always go back, right? Everything we were doing was just rephrasing the same thing in an equivalent way. Now it's a one-way road. Once you've done the approximation, you have a system which is different from the original one. So I would argue that that's where geophysical fluid dynamics lie. And in fact, this red arrow is a bit can be a dangerous path, and many accidents can happen along the way. So and typical accidents are the non-conservation of energy, momentum, or potential vorticity. So there are well-known examples. For instance, one of them is discussed in this paper by Phillips. So this is so you can have all these accidents. If you're a very good driver, you can take care of everything and come up with a model that conserves all that you need. And we have had many of them, like Charney, Phillips, Rosby, Agura. Okay, if you're not a good driver, I have some good news. There's also a safe path, right? So there's a safe path. You go on the race, and nothing can happen to you. You'll always conserve everything that needs to be conserved. This path has been paved for us some time ago. So this started with early mechanics. So this is all based on variational principles, Hamilton's principle of least action. So this was really developed for, say, solid and point mechanics in the 18th, 19th century. Then Noether demonstrated the link between the existence of a variational principle, the symmetries of the Lagrangian, and the existence of conservation laws. And later this was applied to fluids. And more recently, this has been also reframed in a very general and elegant and abstract way by Marsden and Holm and others, using tools from differential geometry, Lie groups, and so on. As far as I know, Ecole is the first one, but maybe I'm missing this point.
Sorry, what did you say?
For compressible fluid? Okay, so in short, how it works, so this is your equation of motion, and you will write an action somewhere. Somewhere there is a variational principle, which I don't write. And you end up, you derive from this variational principle the general form of the equations of motion, which look like an Euler-Lagrangian equation with an extra term, which is related to variations with respect to density. So the action depends on, it's an integral of the Lagrangian. The Lagrangian itself depends on position, velocity, density, rho is density, and transported quantities, like in this case I just wrote specific entropy, but you could add moisture, salinity, and other stuff depending on applications. Okay, the Lagrangian itself will contain kinetic energy. There is a gyroscopic term whose role is to generate the Coriolis force, and a familiar term which is made of internal energy. Here it's written in terms of the specific volume per unit mass, which is the inverse of rho, specific entropy. So that is internal energy per unit mass, and that is the geopotential, which is also potential energy per unit mass. Okay, so at this point, again, you have done nothing new, but you're in a position when you can make the approximations in the Lagrangian itself instead of doing them in the equations of motion. And if you do this, so the equations of motion will remain these ones. L will change according to what you think is best, but you have the guarantee that you can always derive just from this general form of the equations of motion important things, like you know which momentum is conserved, you know have an expression for the energy that is conserved, you have a flux form for these conserved quantities, you can derive a so-called curl form, also known as Crocos theorem, from which you can derive the conservation of potential vorticity, then move on to the Hamiltonian formulation, and if you like, obtain energy conserving schemes. Okay, so you are on a safe road, and at the end of the road, you always arrive at these conservation properties. Okay, so this is also useful to organize the jungle of approximation that you can find in the literature that is used in atmospheric and oceanic models. Okay, so you can organize this in terms of these geometric approximations. You can horizontally put the more dynamical approximations that I have mentioned. And everything is fine and good. So there's no question to answer, right? Everything is fine. We're doing the right thing. And provided we stay on the safe path. So what I'm going to explain now is that even if you stay on this safe path, strange things happen more or less unnoticed. So they happen a little bit under the hood. And I will talk about geometric approximation specifically here. Okay, so if I come back to my geopotential, the surfaces of constant geopotential are they're almost spheres, but they're slightly elliptical because of the rotation of the planet. Okay, but because the ellipticity is small, for the Earth it's 1/300, you can pretend that the surfaces are spherical for practical purposes, and especially when you compute distances, right? When you compute distances, you will introduce coordinates, psi, and you will need a metric tensor to convert increments in the coordinates into distances in meters. And if this surface is approximately a sphere, then the metric on that surface looks like that. R would be the radius of that sphere. And then I have a radial coordinate r, which gives me the distances in the vertical direction. And I can do something similar for my gyroscopic term, which is a linear term, or it's not quadratic, and do something like this. So this is called the spherical geoid approximation. All models in the ocean and atmosphere do that. But so once you have done that, the geopotential now has a spherical symmetry, so you can retro-engineer the corresponding gravitational potential, and it's quite clear that it cannot have a zero Laplacian, which is the Newton's theory of gravity, right? In the vacuum, if you don't have mass around your object, then the gravitational potential should have zero Laplacian. So by introducing this approximation, which is a very good approximation, you violate Newton's laws of gravity. And another approximation, which is very common, is the so-called shallow fluid approximation. So on this picture, you can barely see the atmosphere, right? The atmosphere is 1/100. The thickness of the atmosphere is less than 1% of the radius of the planet. So that suggests to actually replace this squared radial coordinate by a constant, right? So everybody's happier with constants than with variable coefficients. So you can do that. So you replace the metric by this one. And now you live in a space where the spheres that correspond to different altitudes, they all have the same surface. Okay, so you have concentric spheres all having the same surface. So this is a three-dimensional space with curvature, with intrinsic curvature. And also you don't have any translational invariance anymore. So your space is not the flat space that Newton was living in, right? Where you have homogeneity of space. This is lost here. If you do this, right, for the metric, you have to do something similar for the gyroscopic term here. And the simplest idea is to replace r with a constant. That's so-called traditional approximation. It's done here. When you do that and you compute the corresponding Coriolis force, you see that the Coriolis vector, is aligned with the local vertical. While in the full system, you had two components. One is a vertical component, and the other one is a north-south component. So you've lost this one by doing this so-called traditional approximation, which was done by Laplace in his theory of tides. Okay, so if you don't like losing the extra coefficient, you can push the expansion here to the next order. So you replace r by a plus z and take the first two terms in the expansion. So that's what's done here. And then you compute again the corresponding Coriolis vector. So you're happy because you have recovered the missing part here. So you have a non-traditional model. And you have some correction here. And this correction implies that this this Coriolis, the curl of R, it's still a curl, right? It's still non-divergent, but you cannot go back change frame again to place yourself again in an inertial frame. Okay, because when you change frames, all you can do is to add a solid body rotation, and this vector field is not the curl of a solid body rotation. So you cannot cancel the Coriolis force by a change of frame. You cannot go back to an inertial frame with this Coriolis force. So this model has no inertial frames. There is no frame in which you can cancel the Coriolis and the Coriolis force. So maybe we did this with a student, Marine Tar, back a few years ago. So maybe we were wrong. We produced an inconsistent model, but in fact, we had an excuse because other people before us did that. Right? The same defect is shared by the beta plane approximation. Okay, so it's an approximation where you work close. So in this case, I took the equatorial beta plane. So you work close to the equator. So you approximate, you linearize the expression of the Coriolis parameter as a function of latitude. So you end up with this system, and this system too has no inertial frames. Okay, so this has been going on for a while. Okay, so the conclusion is that in fact some geophysical models are not exactly equivalent to Newtonian classical hydrodynamics observed in a rotating frame, right? So it's slightly different. It's a little bit different. So so the emerging picture is like this. So we came from classical fluid dynamics. We knew what we were doing. We thought we knew, right? We have Newton's law of gravity. So space is flat. We have inertial frames. And then we did some approximations. We entered the world of geophysical fluid dynamics, and it seems that all this it's not always lost, but there are examples of loss of each of them. So it seems that we went from the serious world of Sir Isaac Newton, and we are building a fancy world where anything can happen, like in Alice's rabbit hole. Okay, so is that true, right? Is that really the picture that we are making, or are we still on the serious side? So that's really the second part. Where I'll try to answer this question are geophysical fluid dynamics Newtonian. Okay, so to do this, I will first focus on free fall. So I would put the pressure force aside for a few moments to concentrate on free fall, so that's motion subject only to gravity. Okay, so Newtonian free fall, it's well known, acceleration plus gradient of the gravitational potential. It obeys an Euler-Lagrange equation due to this Lagrangian, kinetic energy minus potential energy. You can rewrite this in curvilinear coordinates. So you would define the contravariant velocity components as the Lagrangian derivatives, right? The material derivative of position of coordinates. So this dot is the material derivative. So if you do that and work out the algebra, you end up with basically exactly this equation written in curvilinear coordinates. But now you have these Christoffel symbols which express the metric of the space. Okay. So capital G is the metric tensor. Here it's the contravariant one, which is the inverse of the covariant one, which is here and here. So what we can say about this setting is that space is not empty, right? Space is equipped with a metric tensor. For certain choices of coordinates, the metric tensor is just diagonal. These are the Cartesian coordinates. In that case, the Christoffel symbols are 0. But in general, we have Christoffel symbols. And we have a notion of inertial trajectories, and there are straight lines. They're geodesics of the metric, of the spatial metric. Now, if we go to the geophysical setting, So as I explained, we moved from the inertial frame to the rotating frame, and it's very easy to do in the Lagrangian. You just substitute x dot for x dot plus r, and by expanding kinetic energy, you obtain the gyroscopic term and also the centrifugal term. Okay, so it's very similar to the previous one. The only new thing is that first we have the curl of this planetary velocity, right? R is the solid body rotation of the planet. And now we are taking the gradient of the geopotential instead of taking the gradient of the gravitational potential. But because we know that there are inertial frames, or at least we derive this from motion in inertial frames, we consider the Coriolis force as a pseudo-force, right? It's an apparent force that we think is here if we observe the motion, but it's here only because the frame is not inertial. And geopotential is a bit of a mix because it lumps together the gravitational potential, which is a real force in the Newtonian thinking, and the centrifugal force, which is a pseudo-force. So it's something a bit hybrid. So this, to better discuss that, it's interesting to also write down the free fall equations in a setting where gravity is entirely an apparent force, which is a relativistic free fall. So in relativistic free fall, so from the point of view of relativistic motion, gravity is a pseudo-force. Right, so free fall it's a inertial trajectory. It's a trajectory of a parcel which is not subject to any genuine force. So how does it work? So you have time as an extra. Well, you have an extra coordinate, right? You don't have any absolute time. You have an extra coordinate x0. So you work in space-time. In space-time, you can draw curves. And along those curves, you can compute the intrinsic time, the proper time, provided you are given the space-time metric, g mu nu. And now, the time spent along that curve can be different from the time spent along this curve. Okay, while in the classical world, the time between two events, right, depends only on the two events. It's the difference between absolute time here and absolute time here. Okay, in relativistic world, we can be here at the same time, have the same clock, and then we live our lives separately, and we meet again later, and our clocks don't show the same time. Okay. So regarding free fall, this space-time metric gives us how fast the time elapses along a world line, but it also gives us the free fall trajectories. And the free fall trajectories are those that minimize this length, this proper time. So the equations of motion of free fall will be geodesics. Okay, with this gamma being Christoffel symbol, but now in space-time instead of being in time only. Okay, so can we connect all the three points of view? In fact, this has been attempted before. And the key component is to work on the connection here. So the Christoffel symbol, they define an abstract object called a connection. And can we cast the classical freefall in the language of relativistic freefall? And it's actually done. It was done in 1923 by Cartan. And it's actually a very simple process. So first you decide that the first coordinate, the 0 coordinate, will be time, which is absolute time. So the corresponding contravariant velocity component is just 1. And now everywhere you need, you can just multiply things by 1, especially in this term. And now this whole term is bilinear in the velocity. Okay? So it has the form that we have here. So you can define a metric, small gamma, which is now in space-time, a connection in space-time, which describes, for which the free fall trajectories are geodesics. And there's the real goal of Cartan, I'm not going to talk about that, was to then continue and look at the theory of gravity, right? But I'm not going into this business. Okay, so can we do this job not only for the classical equations of motion, but for geophysical free fall? Well, yes, it's exactly the same trick. So Cartan did this, and we will do this for the Coriolis force. So now everything is bilinear in the velocity. So we have just defined a space-time connection for which geophysical free fall trajectories are geodesics. So we have defined the connection, but in the relativistic setup, the connection is derived from the metric, from the space-time metric, which is the main background field. So can we do something similar? Okay, and so what would be the background fields in the geophysical and classical case? So one step is first to put together, to realize that in the action, right? So that's the action. Did I write the action somewhere? Yeah, okay. So this is the action, right? This is kinetic energy, this is the gyroscopic term, and this is geopotential, so potential energy. So I can play the same game as that I played in the equations of motion. I can play that same game in the action. So now the action is a quadratic expression in the velocity. So I have just put together a covariant tensor, which defines my Lagrangian. So the tensor puts together the metric, the usual metric of space, the covariant components of the planetary velocity, and also the geopotential. Okay, so I have, so this is a candidate to be a background field in four-dimensional space. Okay, so what I would like to do is to draw arrows from left to right. So left is the relativistic case, and right is the classical case. So in the classical case, if I choose time as my first coordinate, then dt is dx0. And if I change coordinates, what I will have is that I will have the derivatives of time with respect to coordinates times the increments in coordinates. Okay? This is the standard definition of velocity components, and a consequence of these two is that I have this constraint on the velocity components. And on the left, I have different constraints. So I would like to draw arrows from left to right. So for the first three lines, I can come with an expression of g mu nu that exactly equals the left to the right. And this expression is this one, okay? So if I just substitute this here, I will obtain exactly the right-hand side expressions. Okay, so I have a first way to connect the relativistic setup to the classical one. Sorry, this is, so I have now time. Okay, usually we have time which is the first coordinate, okay? That's what we do usually, right? When you do classical mechanics, there is no real benefit of using anything else than time as your first coordinate. But if you want to write down things that are independent of the choice of coordinate system, what you will do is that you will have time which is a function of all your four coordinates. Okay? We are in a world where time is an observable quantity. And so when I do two world lines, Okay, so in the first picture, the time would be just my first coordinate, or that depends. Okay, so here I would try something like this. Okay, then this is my coordinate xa1. I have my word lines. Okay, so these are lines of constant time, and the interval only depends on the endpoints. Now, if I change coordinates, now xi0 is not time anymore, so I don't know, maybe my word lines look like this, but I still have something which depends on coordinates, which is time. Okay? And so T mu is just d mu dt over d xi mu. Okay? So dt is T mu d xi mu. Okay. So that's the first relationship, but the important thing is that time exists, right? It's a field. It's one of the background fields. Okay, so if I do this, I can connect the first three lines to the from left to right. But for the action, of course, if I just do what is written here, then my d tau is equal to dt. And then this integral is just the time interval between the endpoints and doesn't depend on the path anymore. So by design. So to connect to the action that is driving the free fall, I have to introduce somewhere my tensor here. Okay, so it's actually simple. You just add it here. So you construct this metric tensor, and then you let the speed of light go to infinity, which is what you expect, right? The classical limit is when the speed of light is infinite. So when you do the expansion, so the first term does not contribute to variations of the action, and the second term will give you exactly this term here. And similarly, you can do the algebra and find that the Levi-Civita action, the Levi-Civita connection tends to the connection that I have defined previously. Okay, so what we are progressively doing is that we have defined a connection for geophysical space-time, and now we are able to derive it from the background fields, which are this tensor that I've described, which packs together the metric, the Coriolis force, and the geopotential, and also time. Okay, and these are auxiliary fields that you can deduce from time and the metric-Coriolis-geopotential tensor. As a side note, which will be useful later, you have some geometric identities associated to that. So when you define a covariant derivative from a connection which is metric, then you can prove, it's classical, that the metric has a vanishing covariant derivative. The metric itself, the metric tensor, or its determinant has a vanishing covariant derivative. So when you take the limit of infinite speed here, you will be able to derive not the same geometric identities, but kind of inherited geometric identities that will be useful later. Okay, so if I summarize where I am now, yeah. So I have, of course, this was known before, right? Relativistic spacetime is shaped by one background field, which is the spacetime metric. And similarly, we can say that the geophysical spacetime is shaped by two background fields. So one is time, as discussed here. And the other one is a covariant tensor. It's not exactly, it's morally it's morally the equivalent to the spacetime metric. It plays a similar role, but it's not a metric tensor, right? So it puts together the geopotential Coriolis, and the spatial metric. So these background fields, from these background fields I can define a connection, and this connection defines freefall trajectories. And the geophysical case is obtained as a limit of the relativistic case. And Newton-Cartan is a special case of the geophysical case. Okay, so now we have a good understanding of how things are placed between purely Newtonian, geophysical, and relativistic in terms of free fall. And now is the moment to put pressure back and internal energy and so on to talk again about fluids. Okay, so for fluids, in the relativistic case, you can derive an equation of motion which states that the covariant derivative of the covariant divergence of energy momentum tensor is 0. That's a very fundamental identity. And in fact, you can do algebraic manipulations and do the same for the geophysical models. So this is also true with a different expression for this tensor for geophysical models. But deriving by just algebraic manipulation is not very satisfactory, because in the relativistic case, this is really a consequence of Noether's theorem. Okay, this is the consequence of the fact that you have a least action principle, that the action is invariant with respect to changes of coordinates, and you also use the geometric identities I just talked about for the derivation. So can we do something similar in the geophysical case? The answer is yes. So we need to be able to work out a variational principle. So this is how it works classically. Okay, so you have, if you take the Lagrangian viewpoint, you have a trajectory, and then you perturb that trajectory by an amount psi, and this amount psi will tell you how much the velocity changes. Now, if you want to do the same thing in a Eulerian frame, you have to convert this psi into perturbations of S, which is the entropy field, and velocity. And when you do the algebra, you end up with these formula, which are in the form of Lie derivatives, right? I think this has been explained before. But as written here, it's not space-time covariance, so you cannot use that to identify the link between the relativistic and classical situations. So what you need is a covariant expression of the transport equations. And this is, this is the mass budget written in curvilinear coordinates. And you see that I can define a current where the spatial components are just the mass flux, and the time component is the pseudo-density itself. And then this mass budget is just the statement that this current is non-divergent in 4D space. Okay, so the short story is that we are not going to describe the flow separately by its velocity and its density. We are going to describe it by a current which is non-divergent. And then you can take variations on this current and find that it's, the variations are in Lie form. You can deduce these variations from the known ones and obtain them in 4D. And they are in Lie form as well. Okay, so that with this way you can work out a variational principle where all the metric, all the background fields are in the Lagrangian, but not in the variational principle itself. So you can apply it indifferently to the relativistic or the classical case. Yeah, I'm trying to go forward. So in the relativistic case, the action is just the integral of the energy. The energy, if you want to connect to the slow velocity limit, right? This is Einstein, E equals mc squared. So the first term is the rest energy. The second term will be the internal energy per unit volume. And then when you work out everything, you can find that the relativistic action, as you go to, as you let the speed of light go to infinity, reduces to the geophysical action. Okay, you have a so-called Cartan-Lichnerowicz form of the equation, which is common to all systems. And you can use your Noether's theorem to derive the vanishing divergence of the mass-momentum tensor. So you can obtain this mass-momentum tensor by the same arguments in the classical case as in the relativistic case. So the final picture, that's almost my final slide. I have one extra slide after this one. Okay, the results. So geophysical spacetime is shaped by two background fields, time and the geopotential Coriolis metric tensor. They define a connection, etc. I've told that before. You can work out a common variational principle for all the different configurations of hydrodynamics so that you can take the limit from one to the other. And so the main strange thing in the end is that you can, even in a classical context, you can consider the gravity as a pseudo-force, right? You can include it, you can hide it in the connection so that in your mass momentum tensor, you only have momentum and pressure. Okay, so gravity is nowhere here. Gravity is in the Christoffel symbols of the connection. Okay, so that leads me to my final slide, where I will provide the answer to the question, or my answer to the question. Okay, so what is really common and what is different between Newtonian hydrodynamics and geophysical hydrodynamics? So I would argue that fundamentally the structure of the equations of motion is really the same, right? We can write them into this Cartan-Lichnerowicz form, which is identical to the curl form or the Croco theorem. We can write down in terms of the divergence of a mass-momentum tensor. So this is really common. What differs between strictly Newtonian dynamics and geophysical dynamics is what we put in this tensor, right? The metric, the Coriolis, and the geopotential. Okay, so I would say that because these are the fields that shape space-time, they really define the gravitation theory that you have behind, which we consider here as given, right? We're not in the business of gravity, we're in the business of understanding the dynamics that result from a given gravitational field and a Coriolis vector and so on. Okay? So I would say that this is dynamics, this is our business, and setting up h mu nu is the business of a theory of gravity, and it's not our business. So we take it as a given, or we can do approximations in it. We don't really care whether we slightly violate an underlying gravitational theory. Okay, so when we do geophysical models, we are still in a classical setting. The time is absolute. But we may violate slightly because we do asymptotic, so we introduce small errors. We may violate slightly Newton's laws of gravity, understood here in a slightly wider sense than usual. So it's not only that the gravitational field has a zero Laplacian, but it's also that space is flat and that we have inertial frames. All three statements are part of a theory of gravity. Okay, so in that sense, I think geophysical dynamics is Newtonian.
In addition to the list of people that you had, Phil Marston, Darrell Holm, for the Lagrangian approach, Hamiltonian approach to fluid dynamics in the rotating case, you should also put Rick Salmon, who did most of it in the 80s. including the relabeling symmetry leading to potential vorticity.
Rick
Rick Salmon, who did that.
I didn't put Salmon.
No, and he did this almost 20 years before then. That's all.
Sure. Yeah, it's hard to put all the name, but you're right, it's an important one.
At some points you have shown the beta plane approximation and saying that there is no inertial frame. I'm not sure if it's the correct way to say it. And then, now that you say you conclude this, I mean, would there be a better approximation for the equatorial dynamics than the equatorial beta plane that would be better from a geometrical point of view?
But you can always do a more accurate approximation, you mean? What do you mean by better?
I am looking at how this remark, which is very interesting conceptually, might also be useful. For instance, when you are looking at approximation. So you have discussed this beta plane approximation, for which you explain that it might not be correct from a geometrical point of view, if I understood well.
No, I think it's perfectly right. I think it's not a problem not to have inertial frames. Because we accept, I mean, if you introduce something new in the model, you have to break something somewhere. So here I'm just trying to draw the limit of what we accept to break and what we don't accept to break. What we don't accept to break is the overall structure which is written here, right? So if we don't have this kind of equation, then we are not doing any classical fluid dynamics anymore. We're doing something else. But within these limits, we have a lot of freedom to do approximations on the background field, on this h mu nu. So these manipulations might have these kind of side effects, like introducing curvature, destroying inertial frames, or introducing a gravitational potential that doesn't obey Newton's law of gravitation, but I think that's something that is acceptable. And I mean, people have been living with this for decades. Nothing. The problem is if something emerges from the model that you cannot interpret. Okay, we do models to obtain explanations about the real world, so we ask from them that they have interpretability. So that's why you can't accept that energy is not conserved, right? Otherwise, something can emerge. It doesn't cost any energy to make it emerge. But this is all guaranteed. So I think beta plane approximation is just fine.
Thomas, that's very nice. I'm sure you've heard the question that follows before, so you must have a very good answer for it. It's all really intellectually very satisfactory stuff, but in which way do you think it does make a difference? In other words, it's related to Freddie's question. You know, it's a little bit like Gödel's incompleteness. I mean, no practicing mathematician has been greatly bothered by it. Okay, so...
Well, physicists might be bothered by the fact that you have models without inertial frames, right? I mean, it's really a cornerstone. That's how you learn this. When you learn geophysical GFD, you are told, okay, these are the equations in an inertial frame, then we move to a rotating frame, and then we do some simplifications, and that's it. We live in this world. So is this world a good world to live in and to do physics and mathematics?
What would you do differently in practice?
Well, in fact, there are at least one people, and it happened to be my reviewer on one of the papers, who didn't accept the fact that you could derive a model without an inertial frame. So he just rejected it as a physically inconsistent model. Okay, so I think I'm like you, and most people are like you, right? They are not really frightened by the perspective of these small defects, right? Having a little bit of curvature or a little bit of or not having inertial frames, but apparently that's not everybody. So I think maybe if that can reassure people who...
No, they're not like me because I'm quite duly impressed. But again, what would you do in your practice of GFD differently, knowing what you just told us?
No, I would actually, that actually reassures me on the fact that I'm doing the right thing.
Okay, last question and then the rest.
Coming back to practice, does it help you find numerical schemes to do?
I don't know.
Okay.
I don't know, because if you keep, if time is the first coordinate, then it's really exactly the same thing as what we had before. So that if there is a reason to not use time as the first coordinate, I don't know, to have some, that's the only direction where I think this formalism could help you. But in terms of practical applications, I'm not claiming this has practical implications.
Okay, let's thank the speaker again.